All right, let's talk about spherical mirror reflection. We have two types of mirrors that we're going to be looking at. We have concave mirrors and convex mirrors, and they appear the same, but they are not. A concave mirror is a portion of a sphere, so if you can picture this as one big circle, spherical mirrors would be one portion of that. And the concave style is where the mirror or the reflective surface is on the inside of that portion or within the cave. And a convex mirror is where the reflecting surface is on the outside. They will have two distinct types of images that form from them, with concave mirrors showing the most variation. Let's talk about light rays that come from very far away. If I take a tree here and I've got its light rays that are bouncing off that tree, and I look at how those rays reflect, there's really, again, an infinite number of these. They're all over the place, but I'm going to look at just these four here for curiosity's sake. The further away we get from these rays, the orientation the rays are to each other appears more and more and more closer to being parallel. If we were to look at just this segment down here, pretty far away from these rays, we've got more or less parallel lines. But when you look at, say, this segment much closer, they're certainly more divergent. They're not parallel. And this is a rule that you need to understand, that when light rays are coming from a very far away, what we will call an infinite distance away, which is not really infinite away, but far enough away, the light rays will always approach your eyes parallel to each other. And so there's something that's very important to recognize for spherical mirrors. All spherical mirrors, the light rays that are parallel, or the ones that come from afar, will always reflect off that mirror such that they all pass through a common point. If I had more arrows that I drew at various different locations parallel, they will all reflect to the same point. And that point is what we call the focus, or the focal point. It is a certain distance away from the mirror, a distance that is known, but it's specific to that mirror itself. And it also happens to be equal to half of the center of curvature of the mirror. So if I were to take this mirror and draw the entire circle of that mirror that I had earlier, the dead center of that circle is what we'll call the center of curvature. F, the focal length, is half that distance. So if I know a mirror has a center of curvature of 6 centimeters, it will have a focal length of 3 centimeters. And that means parallel light rays will focus 3 centimeters in front of the mirror. Turns out, though, that in real life, this doesn't necessarily happen. As this mirror gets bigger and bigger and bigger, or as we get closer to the edges of that mirror, these light rays tend to focus at a point that's not at the focus. And you can see that in this diagram to the right, that the further away you get from the center line, so way out here, these light rays might intersect a spot closer to the mirror than the ones that reflected at locations closer to that center line. So these lines will focus in front of the mirror. And so this is what we call spherical aberration. And that doesn't only happen due to the shape of the mirror, but it also happens due to flaws in the mirror, or flaws as in either the mirror itself, the material is not consistent, or there are blemishes on the surface itself. So ultimately, in real life, if you want a good reflecting surface, you're not going to use a spherical mirror, you're going to use a parabolic reflector. And this is a reflector that'll be not quite a sphere, it'll be more like an ellipse, that is designed to allow those outer edges to all reflect at the same spot. So everything will reflect the same location. So if you're using reflection to, say, focus an image from far away, you're going to use a parabolic reflector. That's what you find in telescopes and satellites and all kinds of other wonderful stuff. But for simplicity's sake and for understanding the ideal model, we're going to look at spherical mirrors as if there was no aberration. We won't worry about the geometry of parabolic mirrors. Some terms here that you should know before we continue. DI and DO, image distance and object distance. Your image distance is the distance where the image will be formed. Sometimes it's in front of the mirror, sometimes it's behind the mirror. When it's behind the mirror, it's always negative. Object distance is the distance the object is placed in front of the mirror. F is the focal length of the mirror. HI is the height of the image. It's negative if it's inverted. HO, the height of the object itself. M is the magnification. So if HI equals HO, M is 1. If the magnification is larger than 1, then the image is bigger. If it's less than 1, then the image is smaller. Virtual images are always behind the mirror and upright. Real images are always located in front of the mirror and inverted. And this might not make sense to you, but it will shortly. You have 2 equations, or 3 technically, you need to know. You can relate the focal length, object distance, and image distance via this equation. Oftentimes we need to invert our final answer. You're looking usually for F, not 1 over F. Or sometimes you're looking for where to place the object such that its image is located in a specific spot, given the focal length of the mirror. Then we've got 2 others down here. Magnification is the ratio of the image height to the object height, or it's the ratio of the image distance to the object distance, but we do need to negate that, and this is to do with the fact that sometimes those images are behind the mirror, so it's negative of that ratio. When we have a concave mirror or a convex mirror, you're always going to have some rays. For example, let me change this. If I had an object over here, let's say I had, I don't know, just a random shape, and light rays were bouncing off this random shape, you're going to have light rays that are going all over the place. They're going in many, many different directions, okay? Many different directions. But you will always have at least 2 of the following 4 rays that will approach this mirror. And these 4 rays are what we're going to call our principal construction rays. 1, you have your parallel rays. 2, you have your rays that go through the focal point. 3, you have your rays that go through the center of curvature. And then 4, you have your mirror-like rays, which I'll explain via a demonstration in a second. Before I get too far ahead of myself, understand that all mirrors have a principal axis. That's that center line that goes right through the center. Your focal length is always the distance on that principal axis from the mirror, and your center of curvature is twice the focal length. Let me draw a few of these examples for you just so you can know what I'm talking about. The first one is your parallel rays. You'll have at least one ray that will approach this mirror parallel to the principal axis. That ray will always reflect through the focal length, through the focal point. Every single time, your parallel ray will reflect through the focal point. You've got another type of ray that might come from some random location such that it passes through the focal point. It will reflect such that it reflects outward parallel. So it's almost opposite to the parallel ray. You will have another kind of ray that will pass through the center of curvature of the mirror. It will always reflect straight back, as if it bounced straight back at you. Didn't bounce off of any normal at all. And then finally, you've got your mirror rays, which are a little bit harder to draw and a little bit harder to use going forward. But they're the ones that will approach that mirror such that they hit the dead center of that principal axis, and they always reflect completely following the law of reflection. So its reflective angle will be equal to the normal at that spot. And that's why we call it a mirror ray, because it behaves like a plane mirror. Using these 4 construction rays, 2 of them at least, you can always identify where a reflected image exists. And we're going to go through and practice that right now. And so for a concave mirror, we are going to look at 6 different scenarios where you get some unique image reflection. This first one we're going to talk about is what we call case 1, and it's where we place an object an infinite distance outside of C. Because it's an infinite distance beyond C, this one and only one case is kind of unique because all of the rays must travel parallel to the mirror. Because again, when you're an infinite distance beyond C, when you're so far away, those rays will approach this mirror parallel to each other. It doesn't matter how they originally diverted. It was far enough away that by the time they hit the mirror, they're all parallel. So this is a very unique case because quite literally every ray we try to draw will reflect in the same location. And these will all, if you pay attention to your rules, all parallel rays will reflect through the focal point. So for this particular case, and only this case, the image will exist right on the focal point. And so this is a very difficult image to see. Ends up being in one location, and it ends up being difficult to demonstrate on a diagram. So for this particular case, you got to understand that when the object is infinite distance away, the image will be located at the focal point. So a lot of times when we do these construction rays, we have to identify some stuff about the image. So you'll see this image is, well, what is the image? The image is located at F, so it's at the focal point. The image is reduced in size. In fact, it's really tiny. You could zoom in far enough and you might three-dimensionally see an arrow exist right here, but it's going to be really, really tiny. So it's reduced in size. And another thing that you can't tell from this ray diagram that you just need to know, and you'll believe me once we get to case number 2, is this image is going to be inverted. And we know it's inverted because of the final thing. We know it's real. And why do we know it's real? Well, you got to remember the definition of real or virtual. A virtual image, the image appears to exist behind the mirror. A real image, the image appears to exist in front of the mirror. And you can see that spot is indeed in front of the mirror. And so it's definitely real. Well, all real images are always inverted. They will always go together. All virtual images are always upright. Go ahead and draw this. Take your time. Make sure you're having only parallel rays and make sure they all reflect through the focal point. Okay, the next we want to look at is case 2. And this is more significantly more common, and it's going to be a little bit more difficult to draw because we have rays that are not only parallel but are going in all sorts of different angles. You can see what will it turn out to by looking up here. I've got a graphic here that I got from the Physics Classroom's website that helps foreshadow where our image will be, but I want you to draw it yourself. And so go ahead and try to draw this scenario and follow along with me here. What I want to try to do is locate where the tip of this arrow will reflect. We are going to have a little easy job finding the total arrow because the base of that arrow is on the principal axis, and everything on the principal axis will always exist on the principal axis after it's been reflected. And you'll see what I mean once I finish this off. So let's look at the tip of that arrow first. And so what we need to do is draw at least 2 construction rays and figure out where they converge. So I'm going to draw the first construction ray, and it's usually the parallel one. That's the easiest to do. So I'm going to have this light ray, and again, remember there's an infinite number of light rays. At least one of them will approach that mirror parallel to my center line of that principal axis. And this one will always reflect, so it reflects through F. Now if I had an eye looking from afar, my eyeball is just trying to capture all of these light rays. If it's trying to figure out where this image exists, we don't have enough information yet. We only have 1 ray. We always need at least 2 rays to figure out where the image is. I could pick any one I want. I can say this ray just goes randomly, but I don't know how that random ray reflects. I can say that I know at least one of them will go through F, at least one of them will go through C, at least one of them will hit the mirror spot. I'm going to pick one. Let's do the F one. So one of them goes through F, hits this mirror. Remember, the ray that goes through F will always reflect off the mirror such that it's parallel to the principal axis. We now actually have enough information. We have a point of divergence. Our eye will trace both of these rays back to where it appears to diverge from, and they will diverge right from this location here. And so that is indeed where the tip of my arrow is. I can go ahead and do a third construction ray just to prove that, and I'm going to do that, but in the future only draw 2. You don't need to draw all 3. And so I'm going to do the one that goes through C. The one that goes through C literally goes through the center of curvature, and then it quite literally reflects straight back. And once again, that spot is still intersecting where all the other 2 intersected. And so we have enough information to now know that this arrow will flip. The arrowhead is now on the bottom. It's down here, because remember, that's what I traced. And not only that, it looks like it got nice and tiny. And that is something that we need to know. So let's take a look at this. When the object is beyond C, So object is beyond C out here, but not an infinite distance away, so a finite distance beyond C. The image is, well, let's see, it's located somewhere between C and F. It's not in the dead center, it's just in between C and F. So between the focal point and the center of curvature. Let's see, we can see here that the image appears to be reduced, and it is, so it's small or reduced in size. It is inverted or upside down. And for two reasons. Because it's inverted, it's definitely real. And also because it's on the light side of the mirror. It's over here. This whole area, for all of the cases, anywhere there's light is the real side. And if the image is found somewhere back here, it's the virtual side. So since this one's located over here, it's definitely real. Before I go to the next case, I do want to just point that out, that as we get closer to the center of curvature, the image will get further away from the mirror, so it'll also get closer to the center of curvature. Not only that, it'll also get bigger. So I want you to try to think about what you think is the next case. Because if you think about this, when it was way, way, way out here, case 1, the image was at F and super, super, super tiny. Now we're approaching C at a finite distance, and the image also starts to approach C and also starts to get bigger. So the next case, perhaps you can determine, well, the next case is where the object is at C. We're now at the center of curvature. Now let's take a look at this diagram so we can get an idea where the image will be, and you'll see here that the image ends up also being located at C. And if you take your time with this, and you draw appropriately, your image as well will be at C. I will tell you that this is very difficult to nail. It's going to be likely that your image isn't exactly at C. Let's see what we can do. So at least one ray will go parallel, and that one ray will reflect through F. Again, that's not enough information for our eyes to determine where the arrowhead is. So we need another ray. At least one ray will go through F. And that ray will, again, if you follow the rules properly, will reflect out parallel. Okay? Now if you take your time and kind of make sure that these arrows are drawn the proper way, and you're not rushing it. This guy needs to be parallel to my center of curvature, okay, or my principal axis. You will see, again, you have enough information. If I were to draw my eye here, the eye will trace these rays back to where it believes to have originated from. Like I said, this is probably the most difficult to draw because you have to be like exactly spot on to nail this. So I was off by a little bit. I wasn't using a ruler or a protractor. Perhaps you at home will do a little bit better because you're supposed to be using a ruler and protractor for this. But you will get very, very close to what you see in this graphic up here. And you will see that the image is also at C. It turns out it's the same size, so there will be no change to its magnification. So it'll have a magnification of 1. It is inverted, and as a result of it being inverted, and as a result of it being located in front of the mirror, it is real. Okay, so that's it for case 3. Again, let's make sure we recognize this pattern. We started really, really far away. The image was really tiny at F. We started to approach C at a finite value. The image started approaching C at a finite value and got bigger. We're now at C, and the image is at C, and it's the same size. So case 4, you can probably expect the object continues to travel towards the mirror somewhere between C and F. So what do you think will happen to the image? Let's find out. The object is now between C and F, anywhere between C and F. It doesn't need to be the dead center. In fact, I intentionally drew this a little bit off of center to show that. Let's try to figure out where the tip of this arrow is. So again, at least one ray will leave the arrowhead parallel to the principal axis, and it will indeed reflect through F. And again, in this scenario, at least one arrow will travel through F, hits the mirror, well, let me use a solid arrow here. It'll at least travel through F, hits the mirror, and it will reflect outward. How will it reflect? It'll reflect parallel. So far, our eyes were down here trying to figure out where these rays originated from. I didn't extend this ray far enough, so I got to continue to extend this out. And we're looking for that point of divergence, and it looks like it's right here. And so we can see here that the tip of that arrow is going to be way out here. And so if I were to take my arrow, flip it so its head is straight down here, we're going to find out that, as you probably were expecting, as that image approached F, or that object approached F, that image got further and further away, and it got bigger and bigger and bigger. So, image is, well, it's beyond C. It is enlarged, so its magnification will be greater than 1. It is inverted still, and it's still real because it is, once again, in front of the mirror. And here's where the pattern starts to get interesting because, again, we started way, way, way out there. Image was at F. We got closer to C. Image was between C and F and got bigger. Object is now at C. Image is at C, same size. Object is now between C and F. Image is further out, and it got bigger and bigger. It's even larger than the object. So what's going to happen? Well, as we continue to approach F, the image does continue to get further away. It does start to get bigger. Case 5, we're going to place that object at F. And I want to know what is going to happen to the image. Well, let's take a look at it. So the object is at F. Well, we know at least one, and this one is also very difficult to draw. I encourage you to really take your time. We know at least one ray will approach the mirror parallel, and it will reflect through F. Now, I've been drawing the focal ray every time. Well, I can't draw that this time because my object is literally at F. There will be no rays that pass through F because the object is on F. So instead, I'm going to use my center of curvature ray. And this is the ray that we know originates from somewhere over here, passes through the center of curvature, hits the tip of the arrow. So I need to adjust this. If I had a ruler here, I'd be able to line it up perfectly. It hits the tip of that arrow, continues, hits the mirror, and then reflects straight back. And so we get this ray, I should probably use a dash line, we get this ray that extends backwards like so, forever this way. Now, if we were to put my eyes here and try to capture this light and see where the rays appear to have originated from, we trace them back to the point of divergence, right? Well, these are parallel rays. They're never going to diverge. We could trace this way back infinite distance this way, and way back an infinite distance this way, and we're never going to see a spot, if I draw them properly, of course, we're never going to see a spot where they appear to come from. Case 5 is interesting because there will be no image at all. There is no image, there will be no real image, no virtual image, no image, because we will have no focal point, no point in which they diverge from. Another way to think about this is known as a beam of light. This is how we can take diffuse light and get it to reflect outward as a nice beam. In fact, a flashlight is really close to this. If we look inside a flashlight, you'll see a light bulb in here. And I am a wonderful artist, of course. You'll see a light bulb in here, and you'll see the flashlight itself has like a little reflector back here. And this is that parabolic surface. Well, this flashlight bulb is placed at the reflector's F, or really, really close to it. So that light is more focused or less diffuse. And so you get almost a beam of light. I mean, it's not quite a beam, but if you were to look at maybe a spotlight in an auditorium, you're going to get much closer to a beam of light. So again, case 5, no image. Now, case 6, let's again take those patterns into consideration. Case 6, we're going to slide the object inside F. What the heck does that mean happens to my image? This is a unique situation. This one's pretty interesting. Case 6, with the object being inside F, ends up getting us our one and only scenario where we get a virtual image. How we draw this is going to be a little tricky, so pay attention, take your time, be careful. You're going to take an arrow and it's going to approach that mirror parallel to your principal axes. It will reflect off that mirror through F. Now we could do multiple different construction rays here. I'm going to do the curvature one because I believe that'll be the easiest to see. We'll have one arrow that originates or goes through the center of curvature, hits the mirror, and it will reflect back through, back away through the same direction it came from, extending outward this way. And so once again, our eye, if we were to place it down here to try to see where the light rays appear to come from, we're going to trace these rays back to our point of divergence. And you won't find that spot to exist on the light side of the mirror. So what we do is our eyes think that the rays came from behind the mirror. Now, of course, naturally they don't come from behind the mirror, but they think they do. So you got to extend these rays backwards. Take your ruler, place it down on these rays, and draw a line behind the mirror. And you'll find out that your eyes actually seem to think that the ray came from back here. Now again, it didn't. This is darkness. There's no light over here. But it thinks it did. And so what we're going to do is we're going to find that the tip of that arrow is actually up here. And if you notice, not only is it behind the mirror, but it stays upright, which it should, because this is indeed a virtual image. So when the object is inside F, where is the image? So the image is behind the mirror. You can see in this scenario, it's enlarged. It is upright, and therefore if it's upright, it must be virtual. And not only do we know it's virtual because it's upright, we know it's virtual because the light originated, or appears to have originated, from the dark side of this mirror, which must mean it's virtual because the light never actually existed here. A great example of one of these types of mirrors is a cosmetic mirror. If you were to look into a mirror to apply makeup, you've got to get that mirror pretty close to your face, and it actually makes your face bigger. And that's why they use those cosmetic mirrors, to help, see those blemishes or whatever you want to touch up. All right, that's it. Those are your 6 cases for concave mirror. Real quick recap. Very first one creates an image at an object is at an infinite distance, image is at F. Case 2, object is beyond C in a finite location. Image ends up being somewhere between C and F, small and real. Case 3, the object and the image end up being at the same location at the center of curvature, same size. Case 4, the object is somewhere between C and F, and the image ended up being outside, well beyond C. Case 5, the image was located at F, creating a beam of light, no image at all. And then case 6, the object is placed inside F, creating a virtual image. That's it for concave mirrors. We are going to now talk about the one and only one scenario for a convex mirror. This is the only scenario that happens. Let me grab an arrow here so I can have an object. It turns out that there is only one case. It doesn't matter where we place the object, as long as it's a convex mirror, you will get your image to appear the same way, or at least governing the same sets of rules. But let's think about a convex mirror. A convex mirror has light approaching from outside the mirror, of course, but since the mirror surface is out here, if we were to draw a big circle, turns out that the center of curvature and the focal position are inside the mirror, or on the non-reflective side. So this is the dark side over here. This is the light side over here. And so yes, the focal and the center of curvature are both on the dark side. It's going to come into play when we go to do our rules, because all of those principles that we drew before, principal rays, they still get drawn here, but they're going to be drawn a little differently. So again, there's an infinite number of rays that are coming off the tip of that arrow, but at least one will approach the mirror parallel. Now here's what's different. That ray will reflect amongst F, but it won't reflect through F because the light can't. It's not going to go into the mirror. Instead, it's going to reflect away from F. Turns out that convex mirrors are diverging mirrors. Light rays reflect outward instead of inward. So what you need to do is you need to start the ray that you draw at the focal point and extend it away at that spot where the principal ray hit the mirror. At least one ray will try to go through the mirror's focal. So draw as if it did. But remember, once it actually hits this mirror, it's not going to travel through the mirror. Instead, at the spot where it hits the mirror, it's going to reflect out parallel. Now, when it does that, we do have enough information to figure out where the image is. Our eye has to trace these rays back to where they think it originated from. And you'll notice there will be no point of divergence on the light side. It indeed will be virtual. This image will appear to exist, if I use my program properly, it'll appear to exist behind the mirror. You'll notice that it is right here. And so I can redraw this arrow at that location, tinier and virtual. And so the following rules apply for the only scenario for a convex mirror. The image is behind the mirror. It is reduced in size. It is upright. And it is virtual. This is very much like case 6 for the concave mirror. The only difference is the size. Convex mirrors will reduce the image. Concave case 6 will make the image enlarged. You will notice these types of mirrors are the security kinds of mirrors. These are the mirrors that you'll see inside pharmacies and convenience stores, so employees can peek down the aisles to make sure no one's stealing anything. The person appears to be relatively tiny, but you get a very good field of view. And they use that type of mirror because it doesn't matter where the person's standing. They can be way out here, they can be way down here. They're still going to show up in that mirror. And if you can see the image in the mirror, it's indeed virtual. Okay, that is it for spherical mirror reflection. Learn these rules, understand these cases, and how to draw these construction areas. You will have to do this. Once you practice this enough times, it actually ends up being quite simple. Thank you.